Detroit, 1940. The air hangs thick with oil and metal shavings inside the sprawling Packard Motor Car Company factory on East Grand Boulevard. On a single workbench illuminated by harsh industrial lights sits a dismembered machine that looks more like a chrome-plated sculpture than an engine. 14,000 parts, over 27 liters of displacement, a labyrinth of gears, valves, and supercharger vanes so intricate that no American manufacturer has dared touch it. Ford had taken one look at the blueprints and walked away. Chrysler did the same. But Colonel Jesse Vincent, a 60-year-old engineering legend who once designed the Liberty engine in just 5 days, runs his calloused hands across the cold aluminum casing. He knows what this machine represents. He knows that across the Atlantic, Britain is being bombed nightly. He knows that Spitfires and Hurricanes are all that stand between Hitler and total domination of Europe. And those fighters run on this engine, the Rolls-Royce Merlin, a masterpiece of British engineering that cannot be built fast enough to win the war. What happens next will become known as the Packard 10-month miracle. A team of American automobile engineers will take an engine designed by British craftsmen who filed parts by hand until they fit perfectly, and they will transform it into something that can roll off an assembly line by the thousands. They will build a factory from scratch. They will convert drawings from British third-angle projection to American first-angle projection. They will measure tolerances that Rolls-Royce never bothered to specify. And they will do all of this while German U-boats prowl the Atlantic, sinking the supply ships that could otherwise bring engines from England. This is the story of how a luxury car company from Detroit helped save the free world. This is the story of the Packard Merlin. If you find yourself drawn into the forgotten corners of history, the kind of stories that never made it into your textbooks, then you're in the right place. Consider subscribing to join us on this journey through time. Before we can understand what Packard accomplished, we need to understand why the Merlin engine was so desperately needed. The story begins in the early 1930s when a quiet revolution was taking place in the engineering departments of Rolls-Royce. Their engineers, led by men like Henry Royce himself before his passing in 1933, had been developing a new generation of supercharged aircraft engines. The PV-12 project, as it was initially called, would become the Merlin. The name came not from the legendary wizard, but from a bird of prey, a small falcon known for its speed and agility. The first production Merlin II arrived in 1937, generating around 1,030 horsepower. This may sound impressive, but the engine was just getting started. What made the Merlin truly revolutionary was its potential for development. The basic architecture, a liquid-cooled V12 configuration with a single-stage supercharger, could be refined, upgraded, and pushed to limits that its original designers never imagined. By the time the war ended, the Merlin would be producing over 2,200 horsepower from the same basic design. When war came to Europe in September 1939, the Merlin was already proving its worth. It powered the Hawker Hurricane and the Supermarine Spitfire, the two fighters that would defend Britain during its darkest hour. The Battle of Britain in the summer of 1940 became a contest not just between pilots, but between production lines. The Royal Air Force was losing planes faster than British factories could build them. German bombers targeted aircraft factories. Supply chains strained under constant attack. The mathematics of war were brutal and simple. Britain needed more engines, far more than Rolls-Royce could produce, even with shadow factories opening in Crewe and Glasgow. The British government looked across the Atlantic for salvation. America was not yet in the war, but its industrial capacity dwarfed anything in Europe. American factories had pioneered mass production techniques that could churn out automobiles by the millions. Surely those same factories could build aircraft engines. The problem was finding someone willing to take on the challenge. Ford Motor Company seemed like the obvious choice. Henry Ford had revolutionized manufacturing with his assembly line. Ford factories were among the largest and most sophisticated in the world. In early 1940, the British government approached Ford with an offer to build 6,000 Merlin engines for the RAF and 3,000 for the Americans. Ford engineers traveled to Britain, examined the blueprints, even took possession of a complete engine for study. Then, suddenly, Henry Ford pulled out of the deal. He declared that Ford Motor Company would not supply materiel to any foreign powers involved in conflict. The isolationist patriarch had doomed the effort before it began. The blueprints and sample engine sat in bureaucratic limbo. Weeks passed. British pilots continued falling from the sky, and then in June 1940, Packard Motor Car Company stepped forward. At first glance, Packard might seem an unlikely savior. The company was known for building some of the finest luxury automobiles in America. Their twin 6 and later 12-cylinder cars competed directly with Rolls-Royce for the affections of the wealthy elite. But Packard had a secret weapon, a man named Jesse Gurney Vincent. Born in 1880 in Charleston, Arkansas, Vincent had worked his way up through the engineering departments of several automobile companies before joining Packard in 1912. He was brilliant, relentless, and absolutely unafraid of impossible challenges. During the First World War, Vincent had achieved something extraordinary. Commissioned as a major in the Army Signal Corps, he was tasked with designing a standardized aircraft engine for American military planes. Working with Elber Hall of the Hall-Scott Motor Company, Vincent designed the Liberty Vi-12 engine in just 5 days. This was not a theoretical exercise on paper. Within months, the Liberty was powering American warplanes over the battlefields of France. By the time of the armistice, American factories had produced over 13,000 Liberty engines. That experience gave Vincent a unique perspective. He understood that mass production of aircraft engines was not just possible, it was essential for winning modern wars. He also understood that the key to mass production was not craftsmanship, but precision. Every part had to be exactly the same as every other part. Every bolt had to fit every hole. There could be no filing, no fitting, no adjustment by skilled hands. The assembly line demanded perfection, and perfection demanded ruthless standardization. When Packard received the Ford blueprints and sample engine in mid-June 1940, Vincent immediately recognized both the opportunity and the problem. The Merlin was a masterpiece of British engineering, but it had been designed for bench assembly by skilled craftsmen. Rolls-Royce did not build engines the way Detroit built cars. At the Rolls-Royce Works in Derby, experienced fitters would receive batches of parts and assemble them on workbenches. If a part did not fit, they would machine it until it did. This method produced engines of exceptional quality, but it was painfully slow. Rolls-Royce was producing perhaps 10 or 20 Merlins per day. Vincent knew that Packard would need to produce hundreds. The first task was simply understanding the blueprints. British engineering drawings used a different projection system than American drawings. What looked like the front of a part in a British drawing might appear as the back in an American shop. Every single drawing had to be converted, redrawn by Packard draftsmen in the American style. This was tedious work, but essential. A machinist who misread a drawing would produce useless parts. Then came the problem of tolerances. In mass production, tolerance is everything. It specifies exactly how much variation is acceptable in a part. A shaft might need to be 20 millimeters in diameter, plus or minus 1/100th of a millimeter. If the tolerance is too tight, parts become impossible to manufacture economically, too loose, and the engine will not function properly. Rolls-Royce, accustomed to hand-fitting, had often neglected to specify tolerances at all. The craftsmen in Derby simply knew, through years of experience, how a part should fit. Vincent's engineers had to take an actual Merlin apart, measure every single component, and determine appropriate tolerances through a combination of measurement and engineering judgment. Consider what this meant in practice. The Merlin contained over 14,000 parts. Each part had to be measured, analyzed, and assigned a tolerance. Some parts were simple, a bolt or a washer. Others were incredibly complex, like the supercharger impeller that spun at tens of thousands of revolutions per minute. Getting any of these tolerances wrong could mean an engine that seized up in flight, sending a pilot to his end. The fasteners presented another challenge. British engineers used British thread standards, which were different from American standards. Some fasteners had been further modified by Rolls-Royce to meet specific needs. Packard could not simply order bolts from American suppliers. They had to either source British standard fasteners, which was nearly impossible with German U-boats controlling the Atlantic shipping lanes, or manufacture their own. They chose to manufacture their own. Beyond the mechanical challenges, there was the question of accessories. The British Merlin used SU carburetors, British-made magnetos, British fuel pumps, and British generators. Packard could not rely on a steady supply of these components from across the ocean. The solution was to design American equivalents, accessories that would bolt onto the Merlin in place of the British originals. Packard engineers replaced the SU carburetors with superior Bendix injection carburetors. They substituted more reliable AC Delco magnetos. They redesigned the supercharger drive. They even developed a better main bearing material that would extend engine life. If these details are helping you understand the hidden stories behind famous machines of war, take a moment to subscribe and ensure you never miss another deep dive into history. While the engineering team attacked these problems, another massive effort was underway. Packard needed a factory, a dedicated facility designed from the ground up for Merlin production. The company's existing automobile plant on East Grand Boulevard would contribute, but the sheer scale of the task demanded more. Ground was broken for a new engine assembly facility, and what followed became legendary in American industrial history. From breaking ground to delivering the first engine took just 10 months. This was the Packard 10-month miracle, a feat of construction and organization that matched the engineering achievement inside the factory. The new factory floor was a testament to American industrial philosophy. Instead of craftsmen at benches, Packard installed long assembly lines with conveyor belts that moved engine blocks from station to station. At each station, workers performed specific repetitive tasks. They were not skilled machinists. Many were ordinary men and women who had been trained for just a few weeks, but they did not need to be skilled because the system had been designed so that any part would fit any engine. The interchangeability that Packard had perfected in automobile manufacturing now applied to aircraft engines. The first Packard-built Merlin, designated V1650-1, ran successfully in August 1941. It had taken approximately 14 months from Packard receiving the blueprints to a running engine. This was remarkable speed by any measure. The engine closely mirrored the British Merlin XX, featuring a single-stage, two-speed supercharger. It was destined initially for American P-40 Warhawks and Canadian-built Hurricanes, but the real revolution was yet to come. While Packard was perfecting its production of the single-stage Merlin, engineers at Rolls-Royce were working on something far more ambitious. The Merlin 60 series would feature a two-stage, two-speed supercharger, a technological marvel that would transform the engine's high-altitude performance. And it would transform something else as well, a promising but flawed American fighter called the Mustang. The North American P-51 Mustang has become legendary, often called the fighter that won the war, but in its original configuration, the Mustang was deeply disappointing. North American Aviation, a relatively young company that had never built a fighter before, designed the Mustang at British request in 1940. The airframe was beautiful, a sleek laminar flow wing design that minimized drag. The aircraft was fast at low and medium altitudes, but it was powered by an American Allison V-17 10 engine, and the Allison simply could not compete at high altitude. This was a critical flaw. The air war over Europe was increasingly fought at extreme altitudes. American bombers flew at 25,000 feet or higher, beyond the reach of most anti-aircraft guns. German fighters climbed to meet them. Any escort fighter that could not reach those altitudes was useless for the most important mission of the war, protecting the bombers that were striking at the heart of the Reich. The Allison engine had a single-stage supercharger that simply could not maintain power at high altitude. As the air grew thinner, the engine grew weaker. Allison-powered Mustangs were relegated to ground attack and tactical reconnaissance roles far beneath their potential. The man who saw what the Mustang could become was Ronald Harker, a test pilot for Rolls-Royce. In April 1942, Harker flew an Allison-powered Mustang and was immediately impressed by the airframe. The aircraft handled beautifully, its range was exceptional, but Harker could also feel the engine struggling as he climbed. At higher altitudes, the Mustang lost speed and maneuverability exactly when it needed both most desperately. Harker returned to Rolls-Royce with a radical proposal. What if they installed a Merlin 61 with its two-stage supercharger in place of the Allison? The two-stage supercharger was the key. The first stage compressed the incoming air, which heated it. An intercooler then reduced the temperature, before the second stage compressed the air further. This double compression maintained the engine's power even in the thin air above 30,000 feet. There was resistance. The Air Ministry in London was skeptical. Rolls-Royce's Merlin production was already fully committed to Spitfires, Lancasters, and Mosquitoes. They could not spare engines for an American experiment. But Harker was persistent. He found an ally in Air Chief Marshal Sir Wilfrid Freeman, who authorized a small-scale trial. 5 Mustang airframes would receive Merlin 65 engines. They would be designated Mustang X. The first Mustang X flew on October 13, 1942, with Captain R.T. Shepard at the controls. The results exceeded all expectations. The Merlin-powered Mustang was not just improved, it was transformed. The aircraft that had struggled to reach 20,000 feet now climbed effortlessly to 30,000 and beyond. Top speed increased by nearly 100 miles per hour. The Mustang had become a world beater. But Britain could not spare the Merlins to put this discovery into production. Every engine rolling off the lines at Derby, Crewe, and Glasgow was already promised to existing aircraft. The solution, once again, lay across the Atlantic. Lieutenant Colonel Thomas Hitchcock, Assistant Air Attaché at the American Embassy in London, had been watching the Mustang X trials closely. Hitchcock was a legendary figure, one of the greatest polo players in American history, but he was also a keen observer of military aviation. He sent detailed reports to Washington, urging the Army Air Forces to pursue the Merlin-powered Mustang. His enthusiasm was infectious. Quoting Rolls-Royce data, Hitchcock reported that the engine change would give the Mustang a maximum speed of 432 miles per hour. There was resistance in Washington, just as there had been in London. The Mustang, as Hitchcock noted with frustration, was sired by the English out of an American mother. It had no parent at Wright Field to appreciate and push its good points. The Army Air Forces were more interested in their own designs, the P-38 Lightning and the P-47 Thunderbolt. The Mustang was seen as a foreign interloper, but the numbers were too compelling to ignore. The Thunderbolt was an effective fighter, but it was thirsty. It achieved less than 1.8 miles per gallon. The Merlin-powered Mustang achieved 3.3 miles per gallon, nearly twice the fuel efficiency. In the escort business, range was everything. Brigadier General Thomas Hayes, a Mustang ace, summarized it perfectly. The Merlin-powered P-51 had the 3 qualities you need most if you were going to escort bombers to Berlin: range, range, and range. Packard received authorization to install their V1650-3 Merlin, the American equivalent of the Merlin 65 with a two-stage supercharger, into modified Mustang airframes. Two experimental aircraft, initially designated XP-78 before being redesignated XP-51B, were prepared for testing. The first XP-51B flew on November 30, 1942, with test pilot Bob Chilton at the controls. There were problems. Early tests revealed that a chemical reaction between different metals in the cooling system and the glycol coolant was clogging the radiator. Engineers designed a new radiator and cooling scoop. The second prototype, fitted with the improved system, performed flawlessly. The marriage of American airframe and British engine was complete. Production began almost immediately. North American Aviation received orders for 400 P-51B fighters from the United States Army and over 1,000 from Britain, where the aircraft would be designated Mustang III. Demand exceeded North Americans' capacity at their California plant, so a second production line was established in Dallas, Texas. Aircraft built there received the designation P-51C, though they were otherwise identical to the B model. The Packard factory in Detroit shifted into high gear. The V1650-3 Merlin was more complex than the earlier single-stage versions, with the two-stage supercharger adding considerable manufacturing challenges. The supercharger's impeller spun at incredible speeds, compressing air to pressures that would overwhelm most engines. The intercooler system required precise manufacturing to prevent leaks. The gear-changing mechanism for the two-speed operation came from a French Farman patent, adding another layer of complexity. But Packard's investment in precision manufacturing paid dividends. The same processes that ensured interchangeability in the single-stage Merlin now ensured interchangeability in the two-stage version. Every V1650-3 that rolled off the line in Detroit was functionally identical to every other. When an engine needed repair in the field, mechanics could swap parts from any available engine without modification. This logistical advantage was enormous. An aircraft that might have been grounded for weeks awaiting specific parts from the factory could be back in the air within hours. If this story of engineering genius and manufacturing miracle has captured your attention, consider subscribing to the channel. Your support helps us continue exploring the forgotten heroes of history. The first P-51B Mustangs arrived in England in late 1943. They were assigned to the 8th Air Force, the organization tasked with conducting the daylight strategic bombing campaign against Germany. The bombers had been taking terrible losses. German fighters, particularly the Focke-Wulf 190 and the Messerschmitt 109, were decimating the unescorted formations. Existing American fighters lacked the range to accompany the bombers all the way to their targets. The Mustang changed everything. For the first time, American bombers could fly to Berlin and back with fighter escorts the entire way. The psychological impact on German pilots was devastating. They had grown accustomed to attacking bomber formations far from enemy fighters. Now, no matter how deep they penetrated into Germany, the Mustangs were there waiting. The Merlin's two-stage supercharger was the key to this revolution. At 30,000 feet, where the air is thin and most engines gasp for power, the Merlin maintained its strength. The V1650-7, the definitive Packard Merlin, developed over 1,470 horsepower at high altitude. This gave the P-51D the ultimate Mustang variant with its distinctive bubble canopy, the ability to outclimb, outrun, and outfight almost anything the Luftwaffe could put in the sky. The numbers tell the story of what happened next. Between January and April 1944, the Luftwaffe lost over 1,000 fighter pilots. These were not just any pilots. 28 of them had scored more than 30 aerial victories. 8 had scored more than 100. These were the experienced veterans, the men who had fought over France, over Britain, over the Eastern Front. They were irreplaceable, and they were gone. A particularly telling engagement came during a mission to Augsburg. German commanders had developed a new tactic using rocket-armed twin-engine fighters to attack bomber formations from outside the range of defensive machine guns. On this day, 77 of these rocket fighters rose to meet the American bombers. P-51 Mustangs dove to intercept. When the engagement ended, 23 German fighters had been eliminated. The rocket fighter threat was over. Mustang ace Harrison Tordoff recalled encountering the ultimate German threat, the Messerschmitt 262 jet fighter. The jets were faster than anything propeller-driven, but they were not invincible. Tordoff spotted two Messerschmitt 262s climbing toward the bombers. He dropped his external fuel tanks and dove. Starting from farther out than he would have preferred, Tordoff opened fire. A single hit on the left jet engine was enough. The German began streaming fuel. Flames erupted. The pilot bailed out, but his parachute did not open. Even against jets, the Merlin-powered Mustang could fight. Thomas Hitchcock, the polo-playing attaché who had championed the Merlin Mustang so vigorously, did not live to see the complete victory he had helped make possible. On April 19, 1944, he was performing a dive test in a Merlin-powered Mustang at Salisbury, England. Something went wrong. The aircraft did not pull out of the dive. Hitchcock perished in the crash. He was one of many who gave everything so that others might fly. While the Mustang gets most of the historical attention, the Packard Merlin served in many other aircraft. The P-40F Warhawk, known as the Kitty Hawk in British service, used the single-stage V-1650-1. Canadian-built Hurricanes flew with Packard engines. Perhaps most importantly, thousands of Packard Merlins were shipped across the Atlantic to power British aircraft. De Havilland Mosquitoes, those remarkable wooden multi-role aircraft, carried Packard engines into battle. Avro Lancasters, the heavy bombers that devastated German industry by night, flew missions powered by Detroit-built Merlins. Even the Spitfire, the iconic defender of Britain, increasingly flew with Packard power as the war progressed. The production numbers were staggering. By the war's end, Packard had produced 55,523 Merlin engines. This represented roughly one-third of all Merlins ever built. Rolls-Royce produced 82,117 at their 3 British facilities. Ford of Britain added another 30,428 from their Manchester plant. Together, these numbers approached 170,000 engines, powering some of the most important aircraft of the conflict. But Packard's contribution to the war effort extended beyond aircraft engines. The company also produced marine engines for the famous PT boats, the patrol torpedo boats that harried enemy shipping throughout the Pacific and Mediterranean theaters. 3 Packard engines powered each PT boat, giving these small craft the speed to attack and withdraw before enemy forces could respond. The Packard 4 M2500 marine engine, a 1,250 horsepower marvel, became the heart of the PT boat fleet. John F. Kennedy, the future president, commanded PT-109 in the Solomon Islands. When a Japanese destroyer rammed and sank his boat, Kennedy's survival and subsequent heroism became part of American legend. The engines that had powered his boat before that fateful night were Packard products. Throughout the war, Packard built 12,700 marine engines, each one requiring the same precision manufacturing that went into the Merlins. The secret to all of this production was the philosophy that Jesse Vincent had championed for decades. American mass production demanded interchangeability. Every part had to be identical to every other part of the same type. This required precision machinery, rigorous quality control, and a completely different mindset from the craftsman approach that had dominated British manufacturing. A story told by Stanley Hooker A Rolls-Royce engineer who worked on supercharger development illustrates the difference perfectly. When Ford of Britain took over Merlin production at their Manchester facility, their chief engineer came to visit the Rolls-Royce works. Hooker assumed the Ford man was intimidated by the tight tolerances required for aircraft engines. The opposite was true. The Ford engineer explained that his company could not build engines to Rolls-Royce drawings because the tolerances were far too wide. Ford built automobile engines with far greater precision than Rolls-Royce built Merlins. Every part on a Ford car engine had to be interchangeable with the same part on any other engine, which required extreme accuracy. That was the only way mass production could work. Rolls-Royce, like Packard, eventually adapted to mass production methods. The shadow factories at Crewe and Glasgow were designed for assembly line manufacturing. Unskilled workers, many of them women who had never worked in factories before, were trained to perform specific tasks. The skilled fitters who had built engines by hand at Derby were redirected to development work and supervision. The butchers, bakers, and candlestick makers, as one historian put it, along with their wives and girlfriends, transformed the trickle of engines into a river of power. The Packard Merlin also incorporated numerous improvements over the original British design. Some of these improvements came from Packard's engineering team. They developed a better supercharger drive. They improved the main bearing material, which extended engine life and reduced maintenance requirements. They used their experience with American production methods to redesign components for easier manufacturing. The Bendix injection carburetors that replaced the British SU units provided more reliable fuel metering. The AC Delco magnetos were more dependable than their British counterparts. Other improvements were actually Rolls-Royce designs that Packard was the first to put into production. The two-piece cylinder block, for example, was a Rolls-Royce innovation that Derby had difficulty manufacturing. Packard's more advanced machine tools and precision manufacturing methods allowed them to implement the design successfully. When Rolls-Royce finally got their version of the two-piece block into production, Packard adopted the Rolls-Royce design in turn. It was a constant exchange of innovations across the Atlantic, each company learning from the other. There was some debate, then and now, about which company built the better engine. The received wisdom in America often suggested that Packard improved upon the British original, building engines with tighter tolerances and better consistency. The received wisdom in Britain sometimes suggested that Rolls-Royce engines were more finely tuned, with slightly higher performance potential. The truth was probably more nuanced. At the squadron level, there were times when reliability varied either way. But when examining large numbers of engines at the group or command level, there was good consistency between British and Packard engines. Both were excellent. What mattered most was that the engines existed in sufficient numbers. The 60,000 engines produced by Packard for the RAF and USAF were of inestimable value. Without them, the Allied air campaign would have been seriously compromised. Fewer Mustangs would have escorted fewer bombers. Fewer Lancasters would have struck fewer German targets. Fewer Mosquitoes would have conducted fewer reconnaissance missions. The entire strategic balance might have shifted. The war ended in 1945, and Packard began the transition back to civilian automobile production. But the company never fully recovered from the war years. The luxury car market had changed. New competitors had emerged. The massive investments in military production, while essential for victory, had diverted resources from automobile development. Packard merged with Studebaker in 1954, and the last Packard automobile rolled off the line in 1958. Jesse Vincent retired from Packard in 1946, having served as chief engineer for over 3 decades. He had seen the company through 2 world wars, developing engines that powered aircraft from the biplanes of 1917 to the sleek Mustangs of 1945. The state of Michigan erected a historical marker at the Packard Proving Grounds, honoring Vincent as America's master motor builder. He was inducted into the Automotive Hall of Fame. He passed away in 1962, 4 years after the company he had served so long ceased to exist. But the Merlin lived on. After the war, surplus Merlins found new homes in everything, from air-racing aircraft to powerboat engines. The engine that had powered Spitfires and Mustangs now thundered around racing pylons at Reno. Modified Merlins pushed unlimited hydroplanes to speeds that seemed impossible. The sound of a Merlin at full power, that distinctive crackle and roar, became a signature of vintage aviation events around the world. The partnership between Rolls-Royce and Packard represented something larger than just engine production. It was a demonstration of what could be achieved when nations worked together against a common threat. British ingenuity and American industrial might combine to produce weapons that neither country could have created alone. The craftsmen at Derby and the assembly line workers at East Grand Boulevard were separated by an ocean, but they were united in purpose. The Merlin also demonstrated the importance of logistics in modern warfare. The most advanced weapons mean nothing if they cannot be produced in sufficient quantities. Germany developed impressive aircraft, from the Messerschmitt 109 to the revolutionary Messerschmitt 262 jet. But German production could never match the Allied onslaught. When German fighters were lost, they could not be replaced fast enough. When German pilots were eliminated, there was no one to fly the planes that remained. The Allies won not just because of superior technology, but because of superior production. This production miracle was built on the backs of ordinary workers, many of them women who had never held a wrench before the war. At the Packard plant in Detroit, as at factories across America, these workers learned new skills and took on new responsibilities. They built engines that flew over Berlin and Tokyo. They built engines that powered PT boats through the tropical night. They were the hidden heroes of the war, their faces unknown, but their contribution immeasurable. The story of the Packard Merlin is ultimately a story about the power of engineering and manufacturing to change the course of history. When Rolls-Royce designed the Merlin, they created a masterpiece of aviation technology. When Packard manufactured the Merlin, they created a weapon of war that could be produced by the tens of thousands. Together, they created an engine that powered victory. The next time you see a vintage Mustang fly overhead at an air show, listen for that distinctive Merlin sound. Think of the British engineers who designed it. Think of the American engineers who figured out how to mass produce it. Think of the workers on the assembly lines in Detroit, many of them barely trained, who built 14,000 parts into a machine that would carry pilots into battle. And think of those pilots, young men who climbed into their cockpits, knowing that the engine in front of them was their lifeline, their source of speed and power and survival. The Packard Merlin was more than an engine. It was a bridge between two nations. It was a testament to human ingenuity under pressure. It was, in its way, a miracle of engineering and manufacturing that helped save the free world. Colonel Jesse Vincent would have been proud. The craftsmen at Rolls-Royce would have been proud. And somewhere, in the fading memories of those who flew and fought with the Merlin's roar in their ears, the story lives on. That sound, the unmistakable rumble of 12 cylinders and over 27 liters of displacement, is the sound of history. It is the sound of sacrifice and determination. It is the sound of engineers and factory workers and test pilots and combat aviators, all united in a single purpose. And it is the sound of the Packard Merlin, the engine that helped win the greatest conflict in human history. If this deep dive into aviation history has moved you, please consider subscribing to the channel and sharing this story with others. History is too important to forget. The heroes, known and unknown, deserve to be remembered, and the stories of their courage and ingenuity should be told again and again, so that future generations will understand what was sacrificed, what was achieved, and what was possible when ordinary people rose to meet extraordinary challenges. The Packard Merlin stands as a monument to that spirit, a mechanical memorial to an age of heroes.